So, all right. So triple integrals, we're doing them kind of quickly, just making a lot of references to the one-dimensional and two-dimensional cases. The two-dimensional is very recent, so we got to see the similarity as much as possible. This part is it's certainly very abbreviated, and technically would have to be, so the definition of Riemann sums would have to be technically on the it never the non-equal lengths to begin with, and an unequal number of intervals on each of the three segments. So A, B, C, D, and PQ, and they might have different number of intervals. So say N, M, and K. Okay, typically, and then you have delta X. I is equal to xi plus 1 minus xi, so give you which one? This length. Okay, then similarly delta y, j is equal to xj plus 1, yj plus 1 minus yj, delta z k equal to zk plus 1 minus zk. Okay, so each length of the interval might be different, just like in the most general setup of the Riemann sum in calculus 1. Okay, so you do not assume that they have to be equal, because it is very easy to end up with something that typically doesn't make sense. Instead, you define it in more general case as possible, and then the theorem is proven that it doesn't matter if your function, for example, is continuous. If the function is continuous, then all of these approaches are equal, and you could actually, you can choose the single n, the number of intervals for each of them, equal intervals, and it will produce the exact same result. But generally speaking, we want to look at it as in a way more general, imaginable. So once again, you cut it in entirely different pieces, x, y, and z y's. Okay, so then you have these points in this box, or rather we have these locations on each of the three axes, x, y, and z. Okay, they cut the each of them gives you like cutting slices in that direction, and then in all three directions you cut, and you end up with cubes, or better. They're not cubical technically; they're boxes, just smaller boxes than the original. And then you produce then the whole thing. Then is called a partition. And then the last step is to you make this partition into a sample partition by adding points within each of these intervals where you sample your value of the function. With this term over here, and then you multiply by what? By the volume of the little box. I guess I don't think I can think of any metaphor for those little things. Like looks like maybe drawers or rooms in a large office building, something like that. And so then that gives you the amount of material. Once again, remember the metaphor is the density. So we sample our density within each of those little cubes and multiply by the volume, and that gives me the approximation of the total mass of this box. Okay, then so that's the Riemann sum. Okay, corresponding to that particular partition, sample partition, and then you take the limit with n, m, and k. Those three numbers increase to infinity in a kind of uniform fashion, so that's just to say they do it simultaneously. It's just not to give it a proper definition. So a better way to define that what's happening is, rather than counting the number of intervals or rectangles, we look at the size of the partition. So the limit is actually is this, the limit over, or limit with delta xk, delta x, delta y, delta xi, delta yj, delta zk, all going towards 0. The maximum of these is called the mesh of the partition. You can define it in a number of ways, either the maximum dimension of those little boxes, or you can take the diagonal. It doesn't matter, it doesn't make any difference whatsoever. The point of it is they are getting smaller and smaller with not just in all three dimensions, okay? And that's how you accomplish this simultaneously. Okay, and then the limit, if exists, give you what we call triple integral, triple often omitted, over b. Okay, so the limit is denoted by triple integral, unless we choose to omit the extra integral signs. And if that limit exists, the function is called integrable over this box b, and so it's supposed to represent give you the mass of the material with f, where f gives you the density. Okay. So, but it could represent other things as well. So, in addition to density, well, density can be understood in a number of ways. It doesn't have to necessarily be in terms of the mass. It could be density of population, for example. It could be density of a particular material within that material. So say density of water within this soil. Okay, so it's not technically the density of the object itself, but rather any particular element within it. And then all kinds of things can be interpreted as density. So it is pretty much close to capturing almost everything imaginable in this respect. Okay, so that gives me the triple integral. And the one thing is worth mentioning here is once again the Flaminian Theory. And that's how to convert the triple integral into three consecutive single integrals. Okay, so f u equal f of x, y, z is integrable over this box AB cross CD cross PQ in R3, right? Then our triple integral over B, f dB, is equal to, and now we consecutively compute three integrals. With respect to these variables, the order once again doesn't matter, so just as well you can go x, y, z in that order. So a, b, c, d, p, q, f of x, y, z. Okay, and now I'm reading from inside out, so they will be in the opposite order: dz, dy, dx. Okay, so that is notation is appropriate because the order doesn't matter. The notation is okay, but later on the order will matter. And these parentheses will make a difference. So this is to make that point. This is it. So that's the first step. Compute the integral of single integral, calculus 1 integral, like it's a partial integration, what we're talking about. So partial integration with respect to z followed by the fundamental theorem, right? So it will be like if you find f, it will be f of q minus f of p. Okay, so let's just do it next, just for completeness sakes. Okay, so and then once you're done with it, then z will be gone, and there will be still two parameters left, and then you do integration with respect to that variable next, like this. Well, next being what? Okay, so then with respect to y, you integrate, the y disappears, you're left with only function of x, and then that's the last integration. So let me carry out this one very quickly, an example of that. So for example, I'm talking about triple integral over a rectangle, say once again, like 0, 1, 0, 1, 0, 1 of x squared minus yz dB by Flaminian's theorem. As you can see, it is certainly integrable with respect to each of these variables, but the function is certainly is. But that's what Flaminian Theory says. So then I'm writing these three integrals in the proper order, even though, well, this happens to be the same. X squared minus yz. The first integration to worry about is dz, then dy dx. Okay, so let me do that. Emphasize this even more. So this is until I'm done with what's in the green circle. I'm not moving on. Okay, so the rest is just parentheses. So I have to get rid of the process will get rid of z. Okay, so I integrate. So I keep this with no change. Dy dz, and what happens inside integration with respect to z, or simply anti-derivative. As you can see, the single integral calculus 1. So I am then integrating. So what am I getting?
Negative y over 2 z squared.
Z, the variable is z. Inside the green circle, we're integrating with respect to z.
Oh, x squared z.
X squared z
minus y over 2 z squared.
Y over z squared over 2. That it?
Oh, plus c.
Plus c. That it?
Evaluated it from 1 to 0.
Almost. All right. Look, take a careful look at C. There's an important point there. Well, I mean, maybe not in this particular problem, but so I'm not going to emphasize that. But let's remember that C depends on x and y. It doesn't matter; it's going to cancel, right? In the next step, it will get canceled, so that's not a big deal. But when you do anti-differentiation, we're going to do it later of functions partially. Okay, the constant every time does not become. It's not literally constant. It's constant with respect to the variable that we're dealing with. So if with respect to z, it is a constant. But the rest of the variables still might be important. So that's why I write cx1. Okay. Certainly, when I do now the fundamental theorem, that part disappears because these are. Let me be careful here. I could write it like this, so there would be no doubt what we're talking about. That these are the variables of c. Okay. So then it doesn't matter what c is; it will be gone. And so, as far as definite integration is concerned, then that constant never really comes into play with any importance. So if you can't skip it, that's not a big deal. Okay. So I plug in 0 and 1. Z. So I'll have x squared minus y squared over 2 and nothing, and then I'm done. Dy dz, right? Okay.
Wouldn't it just be y over 2 instead of y squared?
Yeah, thank you. Y over 2.
Shouldn't it be dy dx instead of dz?
Yeah, thanks. Dy dx. Oops, okay. All right, so okay, so we're done with this. Now we turn to the next variable, which is y. Okay, and so integrating with respect to y, I am getting. What am I getting? Integrating x squared with respect to y. Give me
X squared y.
x squared y. Okay, and then
Minus y squared over 4.
minus squared over 4. Once again, I drop c, so we're doing definite integration anyway, and the limits with y from 0 to y equal 1 dx. I will still circle this. Okay. I do the fundamental theorem, which gives me x squared minus 1/4, right, and then 0. Okay, so then I'm done. I'm done with y. As you can see, there are no y's inside that little circle. And then I just integrate with respect to x, so I'll have x cubed over 3 minus 1/4 x from 0 to 1, and I end up with 1/3 minus 1/4, which is what? Okay, well, I hope I didn't make any mistakes here. So what is that, practically speaking, what we have found is, so imagine you have a box of unit size, okay, so it's a cube, okay, and then some density within it is described by that formula x squared minus yz, so at the location xyz, this is the density. Density at xyz, and then you add them together, and then the meaning of the integral is the mass. Okay, so if you need an interpretation of this abstract mathematical computation, that's what it is. The density function at xyz, and with that density, what is the mass? The integral, the triple integral. Okay, so it is certainly would be a good exercise. Scramble the limits, and instead of going dz dy dx, you could go d dy dx dz or something like that. And the end result is the same, which is might seem surprising considering how different the steps, the intermediate steps, how different they're going to be. Okay, so imagine that I started integrating that original function over there, but with respect to x, I will end up with x cubed minus yzx from 0 to 1, and then it will be, the steps will be totally different, but the end result is the same. Okay, so what else? So that was the triple integrals as we ascend. So once again, remember that these are what we want to learn the most. The steps of raising dimensions rather than any particular dimension in particular. And there is every time there will be something of a reference to the previous dimension. Okay, so that to the previous dimension, to the previous integral. So triple integrals will be referring to double to singles. We did it already many times. And I'm not referring to the Flaminian Theory, which reduces everything to single integral, consecutive integrals. No, it is something more subtle, but this is already what we started with last time. I'll give you an idea of that. So average value of the function, and the average value of the function is like, once again, if you take that metaphor of density, it is the average density. Okay, so how do you find the average density? What is the meaning of the average density of an object? Well, you take its mass and divide by what? Exactly. Either by, if it is a linear density, you divide by the length. Okay, so you take your rod, and you don't know what the density is, but you can find its average density how you take the mass and divide by the length. That will be your average linear density. Now, then there is also density of a thing like a lamina. Okay, so what do you do with it? You take that region, you once again take its mass and divide it by the area. Okay, so that is not a linear density, but I don't think there's a word for it. And once again, that gives you the average value of what? Of the density of that region, and you divide by the area. Okay, so we already certainly can guess what's going to happen in dimension 3. It's the same. This time we're talking about a function of 3 variables, and as a result we have a triple integrals, f dv, and then we divide by, we have now a box, which we just looked at, and it will be b minus a, d minus c, and q minus p, which looks more complicated than it deserves, because this is, let me make this clear, this is a box. So this is a rectangle, this is a box, and I'm talking about the area, the volume of the box. Okay, so length of AB So in fact, just to make that point, let me fix this notation a little bit, the one that we already used. Integration over 8b is segment. So we integral over segment divided by the length of the segment gives you the average value of the function. Okay, now the average value of the function of two variables over a rectangle is the double integral of f over that region divided by the area of that region, plane region, plane box, okay, and plane rectangle, okay. And then we have a box, and then we divide by the volume. The triple integral is divided by the volume. You can see how we can keep going, and that would still make perfect sense. So if you think about, there is really, if we are not speaking of density, which is hard to speak of once you be on dimension 3, but if we're talking about function of many variables, and we still might be interested in its average value, and the average value would be once again computed in a very similar fashion, except over here in dimension 4 you have 4 terms, and then on and on there will be what we're going to be talking about would be n-dimensional volume, whatever that means. And now this all applies to everything has been kind of boxy. Like we spoke of, that image over there is like it's a sandbox, and then with on top of it we have a curved surface. Okay, curved surface, but everything else is straight. In dimension 3, we couldn't even visualize anything curved because the curves. What is curved is the level curves are level surfaces are curved within this box, but it's still a box. And we are, remember what we started with. In fact, this topic is with the volume. The volume of the sphere. Okay, so that is not a sphere. What happened to it? I don't know what I did to it, but that's not a sphere. Well, anyway, well, let me check the formula. Okay, there's some the reference is messed up. Okay, so I don't want to fix it now. So let's imagine that this is what we cared about. You can see that the trouble with computing the volume of the sphere by means of the double integral is that the domain is not a rectangle. Okay, so in general, the domain is not a rectangle in dimension 2, or a box in dimension 3, and so on. So the example is the sphere. So f of xy is equal to square root of 1 minus x squared minus y squared. Domain is x squared plus y squared less than or equal to 1. Okay, so it's a circle, which means that, so if I call this R, domain R, then R could stand for region, and then, but the problem is then so it's not a rectangle, so this double integral that I'm interested in, and that would be very nice if I could do this. This would be the volume, or at least half of it, volume of the sphere, so half sphere, would be this, except, or also all the average values of the function. What is the average? So you have half a sphere of sand, and you might ask yourself, what's the average height? Of such an object. Unfortunately, once again, we are not in the position, so I was looking with something like that, we are not in the position to deal with the double integral of origin other than a rectangle. Okay, so the answer is uncomplicated. We already did that exactly that. So what's the answer? Look how we handled it.
This is the 2/3 pi?
Well, that's the answer. What I mean is how do we deal with the case of the domain not being a rectangle? We did deal with it in this particular example. Remember what we did?
We just considered the values that were undefined as 0.
As 0. So fill the rectangle with 0. I literally did that. Literally. Over here. See, these are inserted by hand. In fact, I missed a few over there. So I first erased all of them, and then actually that's what I did in class. I erased them, which not doesn't really tell the right story, but it's better to fill them with zeros, and then indeed we have a new function which has a bigger domain, okay, and a rectangle domain, any domain we want, and it will be, if you think about it, the volume will be certainly the same. Okay, because those terms, the Riemann sum will be now defined, but these terms will not contribute anything. Okay, so this is how we put it. So define. So that's the definition. So suppose, say U is a region in on a plane, okay? So then the double integral in the function we have then double integral of over U F dA is equal to double integral or G dA, where okay, so once again we replace this integral what's on the left is to be defined. This is up to this point is undefined. So we now explain what it is supposed to be. That's what we replace it with a new integral, new function, new region. So where R is any rectangle that contains U, and by rectangle, I mean the kinds of rectangle that we have dealt with, and that is the one that is aligned with the axes. So if these are the axes, and I have my region U, might be complicated. I put it inside of a rectangle R, like this. So that's my R. Okay, and secondly, now the function is different too. It's the function is G, and I define it piecewise as we have done before. Xy is equal to f of xy if xy is in U, okay, or 0 otherwise. Okay, so it is literally then the graph becomes a surface that was, so let me show the transition, that was sort of hanging in the air. So suppose the domain was a circle, or something circular, then the surface might look like this, right? Looking like this. So that is my F, and then I transition this to what? I add a rectangle first. So that's my circle here, and it's not like it doesn't really do a lot. So that's my rectangle R. Okay, that whatever happens to that surface is really not a big deal. So I still have my some kind of cap, and then what is the graph of G? I'm trying to plot G here, and what is going to have this cap, and then vertical walls, and then flat. Okay, so let me try to. So G, I will have this cap, vertical walls towards the plane, and the values here are zeros. Like this. So vertical walls, you know, they don't really present. You don't have to plot them because it's more like you have a hovering. Excel does that, but otherwise you have a hovering cap, some kind of hat on top of it, and then the flat area outside of that circular region to the all the way to the edges of the rectangle. So that's what G looks like, made of F. It is exactly what has happened here. Well, Excel does that automatically. It doesn't really actually understand the functions of two variables, say, defined on anything but a rectangle. Okay, so that I actually had to. That's why I had to delete those entries in order to, and even then it would still plot something. Maybe. Well, anyway, you can see how you can see the vertical walls, and you see that that blue part is the fill-in. It is a fill-in. It's kind of a nice, but also kind of a silly substitution, because filling things with zeros is really not a big. It's not really profound if you think about it. That's kind of substitution. It's a nice trick how to reduce something more complicated to something less complicated. Okay, so first of all, I don't want to revisit this issue when we do 3-dimension, because what is the difference? What is the difference? So let's quickly take a look at this little development up to this point. What if the domain of a function of 3 variables is not a box? Okay, so what do we do? What is the difference? So I would have a triple integral here. I would have dv there. Okay, so how would I build a function? Well, what would I build a function that we can integrate? So suppose we have a function of 3 variables, and it is, for example, is defined on a ball rather than a box. So what do we do?
You
So
just
suppose-
consider a
what?
box that the ball is contained in, and define it.
Yeah, so put the ball in the box, or rather build a box around the ball. So if you had a ball like this, so you put it in a box around it, like this, and then integrate over this, and that will be the domain of integration. The rest of the rest of the box with the zeros. So whatever the values of the function f were originally inside of that little ball, then you keep them, but outside you fill them with zeros, and that's your new function g, and then you do triple integration of that function over this box dv. Okay, so it works out exactly the same way. So xz, xyz, xyz, that's it. Okay, so that trick can be done in any dimension. The meaning exactly the same. So which means that yes, now at this point we have a chance at least to handle any shapes for the region of integration of any shape, hypothetically any shape. Okay, so that in any dimension except well, we cannot visualize anything beyond dimension 3. Okay, so the point is, one thing is a really nice thing that comes out of it is the ability to use double integrals to handle areas properly. So we think we know how to handle areas, but really we did it in calculus 1. But the proper way to do it is to use double integrals, not single integrals. So dimension 1, once again, this is it. The origin is the problem, of course, was that the origins were sandboxes once again, and now in dimension 2, hypothetically we have no restrictions, so we still have something like this, and the origin could be weird. Okay, and then so origin U say. Okay, so how do we compute the area? That's what I'm interested in, the area of U. Okay, we know how to, that's okay, we know how to handle it. Will be a function of single integral, Riemann integral. Okay, now what we dimension 2, it's actually very simple. Well, if anybody wants to guess. What do we integrate doubly to get the area of U? We integrate a constant function equal to 1, like this. So the trick is the double integrates the volume, but if the width, the thickness of this object that I'm building here, like a pancake, is 1, then it gives you the area. Okay, so I'm taking the same exact thing about it, like this. Okay. So the region lies, that region U is in the xy plane, okay? And then what I do is I thicken it to the width of 1, or thickness of 1. Okay, so the two-dimensional region becomes a three-dimensional solid, okay? And then I compute its volume. So the equation of the top edge of this region is z equal 1. It is flat. It is horizontal plane. All the complexity now is not in the function. The function is so simple, but in the shape of the domain of integration. But so that is a worthwhile trade-off. So the area is that's the way we sometimes write. A U is the double integral of 1 dA over U. Okay. Oh, the usual caveats. Caveats apply. What are the caveats?
It has to be integrable. Has to be continuous.
Well, the function is continuous, right? 1 is continuous. But the integrable, the meaning of integrable becomes different because now the integrability was assumed to be over a rectangle, and now it's not the same as speaking of the integrability over an arbitrary region. And then the shape of the region might matter, and it could be, you can think of example when it is not integrable, and so some of the regions might not have the area. Okay, so that certainly is, for the time being, we have to assume that it is the case. Sometimes we can say that this region has area, and sometimes we cannot. Okay, that's okay. So because ultimately every integral is a limit, and limits might not exist. So. But most of the regions that we care about look like this, and we can always compute their areas. Let's confirm, though, before we start using it, let's confirm that we're producing the same area. That area, we had area, the definition of the area was pretty much this, the single integral over AB. Okay, let's show that it's the same thing. Okay, so we go back to the setting of calculus 1. We have a function y equal f of x. Okay, and then of one variable. Then the area is integral from a to b fx dx. Okay, on one hand. On the other hand, let's see what we're gonna. That's actually the point where we have to start developing the further version, the next version of the Flaminian theory, and that is let me do that. So on the other hand, it is the integral over this region being what is it? Okay, so well U 1 dA. Okay, so we still do not have a way to compute it in any other way using Flaminian theorems. We still don't have it just yet, but that's okay because we're going to go this way, and that will actually tell us what the Flaminian theorem is supposed to look like. Okay, so what is the region U? It is those xy's with x lying between A and B, and what about y?
0 in the maximum.
Well, that not the maximum, because then you would include things that aren't there. This is the maximum of f. That's what you're referring to. Then you will include all of these points too. So what should we write here?
Oh, the average?
No. It's not, U is not going to be a rectangle. So if you want to put their number over there, it is going to be a rectangle. X between two limits, Y between two limits, it's a rectangle. So it will, well, simple answer is f of x. Okay, so f of x, so the restriction on x and y is simultaneously on x and y, not separately on this is for x, this is for y. That gives you a rectangle, but we have to point x, y, and as you can see, there is a region where that upper limit on y depends on x, right? So over here you have one upper limit, over there you have a different upper limit. Okay, so it depends on x, and what is the dependent? Simply f of x. Okay, so all right, so that's good. So we have our region U, and what? And then we then realize what the Flaminian theorem is supposed to look like based on this analysis. So these are equal, supposed to be equal to area computed one way, computed the other way. We cannot confirm it in any other way by the Flaminian theorem that we don't have yet. So what we do is we discover what the Flaminian theorem would look like under these circumstances, and this is what it is. So if region U looks like this, then the double integral over U will be integral from, well, these are the limits. These are the limits. So the limits, these are the limits of integration. So the limits that came from over here, from just the definition of U, once again, where's U? This is my U. This is U. Okay, so we describe U in this algebraic way with inequalities, and the x has limits between A and B. Okay, so I'll just put A and B. Okay, and what we are being integrated is still 1, and we have here dy dx. But now we know the limits, what the limits over y are. 0 f of x. 0 f of x, like this. So limits for x happen to be constant. Some of them should be, and then there are limits for x for y, and they depend on x. Okay, so as you can see, the structure of the formula is very similar to the original Flaminian theorem, but as you can see, the only difference is right here. That's the difference. The limits might be dependent on the variables outside of the parentheses. So if we're still going to integrate with respect to x later, then it is allowable to have limits that depend on that variable. Why? Because then x will disappear, and the answer will be a number, even though the limits are variable, and we certainly haven't done that. But this, if you can verify, if I now start, let's verify this. If I start now carrying out this integration, what I'm going to have, integral from A to B, what's inside the brackets, it will be, I integrate 1, I get what? Y with limits 0 and f of x, right? dx. So that is still what's in the brackets. Applying the fundamental theorem, right? And so I have f of x minus 0 dx, right? And that's it. And then we back to the original integral. So what remains is just to have the Flaminian theorem developed appropriately, in which we already have all the ideas of Flaminian theorem right here. So let's do it one more time. So this is the simplest application of Flaminian theorem when the origin is still like a sandbox, so everything is straight. But let's do the Flaminian theorem for a circle. So the area is a circle, and we're computing. How about we're computing the volume of? Hold on a second. The volume of a sphere. Yes, the volume of the sphere. So what would the Flaminian theorem look like, or Flaminian formula if you prefer? So, sphere, radius 1, okay? So the whole thing looks like this. This is my domain, the original domain, so circle, radius 1. Okay, then we're going to build a box around it, but that's well, I'm not going to build the box, we're just doing the Flaminian theorem. Okay, so, and then the upper crust, if you like, is this. Okay, so that's my sphere, once again, radius 1. Okay, so we're supposed to write it as the volume equal to, it is equal to double integral over this region R, the base circle, okay, F dA, okay. The function will be, as we have seen already, is this. Okay, so region R is now the key step is to convert this double integral into two consecutive single integrals, is to write the region correctly in terms of the inequalities on x and y. Every time it looks the same roughly. The limits for x should be constant, a and b, and the limits for y might be variable depending on x. Period. There is no other way. Okay, so what are the limits for x? Well, let me get it on the xy plane for convenience. So that's my circle. This is my region R or U, negative 1, 1, negative 1, 1. The limits for x are just look at the largest possible values. These are the possible values of x. They will be between negative 1 and 1. Okay, so we are not concerned to begin with. When we start with the last variable we're going to handle, we're not worried about dependence between x and y. So the possible values of x could be any value between negative 1 and 1 is possible. It is the challenge is to deal with y appropriately. And how do you do it? You imagine that you have fixed x. By taking care of the first line over here, I am fixing x. So if this is x, this is x, this is x, okay? And then I just need to, and then I have my integral, right? This is my integral right here. So what are the limits? Depending on x.
Negative square root 1 minus x squared.
That's right, yeah, and then positive. Okay, so and these are the limits of integration, literally. Okay, so we'll do it next time. Finish.